Thank you very much. The pronunciation was correct. So my name is Joseph Piotrowski from Vulcan
Excellent.
Energy. And yes, I will talk about the GeoSmart project. Again, I'm the Geothermal Technology Development Manager at Vulcan Energy. So basically dealing with everything in the context of the geothermal fluid and the surface installations, especially at the INSAM site, which is currently in operation. The project that I would like to talk about is the GeoSmart project, so technologies for geothermal to enhance competitiveness and smart and flexible operation. First, a few words to the project in general. So the problem, or better challenge, is that geothermal energy is poorly developed at the moment in some stages because we have a limited flexibility for the day and seasonal swings, especially in the mix of heat and power generation. And also we have issues with scaling at low temperature brine. So if you want to extract more energy, we need to cool down the geothermal fluid to a higher extent, but then we run into scaling problems. The GeoSmart solution that we offer during the project is energy storage and power block management for the innovations to provide daily flexibility and the so-called dispatchability. The integration of more flexible ORC, so organic Rankine cycle operation, which is used for electricity production, and innovations to extract heat from brine and removing the scale formation. So the overall goal of GeoSmart is to demonstrate two variants of technologies meeting different flexibility needs of a high and of a low enthalpy combined heat and power plant, and to provision to work for the power plants. Um, on the next slide, here we can see who are the project partners. So we have 19 partners, including geothermal operators, research and technology organizations, small and medium enterprises, universities, and also research organizations from Iceland. Let me quickly start the pointer. From Iceland, from Norway, the United Kingdom, Belgium, Germany, France, Italy, and also from Turkey. There are two demonstration sites. One is the natürlich Insheim GmbH in Insheim. This is located in the Upper Rhine Valley in southwest Germany. And the other demonstration site was from Sordo Energy in Kizildere in Turkey. The goals and the project is sorted as the following. So we have four pillars that we wanted to improve. The flexible system operation using thermal energy storage, the wide efficiency for OSC plant operation by approved system control and design, increase the ORC power efficiency using an adiabatic cooling system, which I will explain later on, and removing temperature constraints that I was mentioning before in terms of scaling reduction system. Since we have two operation sites, one in Insheim and the other one in Kieseldere, will focus on the Insheim site as I was involved in this part of the project mainly. The aim is to uh, provide cost benefits, reduce scaling, improve the environmental performance, and the efficiency of the power plant. The energy storage was tailored as per site needs. As we heard before, each geothermal fluid is different, so we have different requirements for energy production, which was considered here. Then improved efficiency of the organic Rankine cycle electricity needs and the innovation to extract heat from brine and removing the scales, which was mainly part on the Kieseldere side. So during my talk, I will focus on the first three columns, so the thermal energy storage, system design and control, and the adiabatic cooling system to increase efficiency. On the next slide, there's a quick overview of the Insheim site, which is currently in operation. We have a geothermal fluid cycle with one production well and one injection well. Both are about 3,600 meters deep. And here we see in the schematic sketch, we can see how Insheim site is operated. So production well with a line shaft pump, which is hanging 700 meters deep, is producing geothermal fluid with a flow rate of about 65 kilograms per second. Temperature is 165 degrees and the operational pressure is 22 bars. This geothermal fluid is flown through a heat exchanger. Actually, there are three heat exchangers, one vaporizer and two preheaters, but for sake of simplicity, only like one symbol is chosen here. Then the geothermal fluid is cooled down and it's being injected into the injection well with a lower temperature and a lower pressure. On the other side of the cycle, the heat is transferred to a working fluid, in our case isopentane. And here we see the pump, which is increasing the pressure of the liquid isopentane. Then it's fed through the vaporizer and the preheaters, and it's vaporized by the heat of the geothermal fluid. Then the high pressure gaseous isopentane is flown through a turbine, which is driving a generator, and this is how electricity is produced. The isopentane is leaving in gaseous form the turbine, and then it needs to be cooled down and condensed, so liquefied again, so that the cycle can restart from the beginning. The power plant is in operation since 2012 with a very high availability, and since 2022, we are part of the Vulcan group, as you can see here in the picture below. So on the left side, you see the engine, 1 megawatt, driving the line shaft pump, which is hanging 700 meters down at the shaft. And on the other side here, we can see very little the injection well. So on the surface, the two wells are very close together, but then they are declined in subsurface so that the tips are, I think, 1.2 kilometers away from each other. Here's a top view of the Insheim side power station. Here is the fence of the power plant, so that's the area that we own. Here are the production wells with this sealed AWSV area. Then the geothermal fluid is flown through the heat exchangers, which unfortunately you cannot see because everything is below the roof. However, we can see pronounced this 30 fans, the air-cooled condenser, which is needed to close the cycle again. On the next slide, I will talk about the innovations of the during the GeoSmart project that were installed. And you see a lot of changes that we implemented. So here's the schematics as it is operated now. And oopala, this is what we did during GeoSmart. First thing was to install an adiabatic cooling system. So we improved the function of the air-cooled condenser. A groundwater well was installed, a purification system, and we spray water below the air, below the air-cooled condenser to cool down the air locally. This is how we can increase power production during summer days, during hot summer days. The other innovation is the so-called innovation cycle. So we took a fraction of the geothermal fluid that was produced and led it here through new heat exchanger modules, cool it down to a similar temperature as before, and then it's re-injected to the main line and back into the injection well. On the other side of these heat exchanger modules, we now have a industrial water cycle. So heat is transferred to industrial water, which is then fed, and it's getting a bit complicated here, through some air coolers representing an OSC unit and an air cooler representing a district heating unit. So with this setup, we want to flexibly supply heat to an ORC and to a district heating. Initially, it was planned to rebuild the entire power plant. However, this was not feasible during the project duration. So we ended up with this solution that you see here now. In addition, you can see a thermal energy storage with a hot and a cold side. So this is always filled with liquid. When we want to charge it, hot water will be pushed on top, from top, and a thermocline will establish, and we can store the hot water by pushing just the cold water out of the storage. If we want to discharge it, simply the other way around. So we feed in cold water and push out the hot water to supply district heating or organic Rankine cycle. The hybrid heat exchanger, so this VT2 here, consists of 4 modules, and it's a new technology that we want to test within the project. So this is a plate heat exchanger, which forms on one side tubes. And this is how we can clean the heat exchanger, or we expect that it could be cleaned, because other tests with normal plate heat exchangers showed that with the geothermal fluid in the upper Rhine graben, this is not feasible. So the aims are for this innovation cycle to provide flexible heat and power, to characterize the hybrid heat exchanger, and to use the thermal energy storage for redundancy at the district heating. On the next slide, I brought a few results from the adiabatic cooling system, and then on the last slide, I will show a few results of the what we can see here of the innovation cycle. So first for the adiabatic cooling system. Here in the picture, we can see the system in operation. So basically, it's those little lines here under the air-cooled condenser where we spray water, which you can see here as fog, and this is then um, vaporizing on the way to the yeah, to the cooling fins of the air-cooled condenser. So the beige lines here, which you can see, the isopentane, the working fluid is flowing through. And here you can see the feed pump of the ORC. Um, exactly, this is how the fogging system is working. And on the left side, you see the temperature over the time. Sorry for the German plot, but I couldn't find another one at the moment. And we can see also the power production in kilowatts also over the time of working of a day where we sprayed some water. In yellow, it's indicated from 11 to 2 o'clock we operated the system, so the water was sprayed. Then we made a break of 1 hour and we started at 3 o'clock again and sprayed for 1.5 hours. What is interesting is the blue line, so we can see the ambient temperature which starts to rise, and at 3 o'clock it's almost constant 32 degrees. So it was a very hot day in summer last year where we conducted this test. And the most interesting thing that we can see is the purple line. So this is the power production, which goes down as the ambient temperature rises, because we cannot, if the ambient temperature rises, less energy is transferred to the ambient and the ORC cycle, the efficiency goes down. This is why we produce less electricity with rising ambient temperatures. As we start to spray, this incline is less. And it's interesting, if we stop to spray, we can see a big jump and we have lower power production. And when we restart the spraying, it jumps up again as long as we spray. So we can really see the impact of the fogging system on power production. And what is even more interesting is that we only sprayed 9 fans, so only a fraction of the entire air cooler field. And we saw an increase of power production of 5%. So this is quite promising, and we plan to do more tests this year in summertime when it's getting hot again to analyze the cooling capacity and also the power production. On the next slide, as I said, I show a little bit about the innovation cycle. So we can see here the hybrid heat exchanger, one module, it's 4 meters long and 1 meter 50 high, and we have a lot of flanges on top and at the bottom. This is because of the cleaning that we wanted to implement. In the lower picture here, we see this plates that forms tube on one side. So we light it with a flashlight from the other side while I took this picture. And this is about, I think, 8 millimeters. So these tubes are quite big compared to 2 or 1 millimeter distance of plate exchangers. And they're arranged in the system that we can clean that from top to the bottom, which we need to test. And in the second picture here, you see the thermal energy storage is a vessel 15 meters high, 90 cubic meters capacity, and designed 14 bars and 170 degrees Celsius. This is our storage for the district heating supply of the village of Insheim. And the curves I will only tackle or explain in not that detail. We can see here the heat demand over a time. These are simulation curves, so it's not measured yet. And you see the variation of the heat demand that is used for ORC production, meaning electricity production. Yeah, this is varying a lot according to the ambient temperature changes. What is interesting is the yellow bar here. This indicates a sudden failure of the geothermal source. That means that we do not get any energy from the geothermal fluid. So we have to use the thermal energy as a redundancy for the district heating. And it seems during this simulation that the level was still enough, even if it was already 20% discharged, we can still provide the energy for 2 hours at least for the district heating. This is usually enough to restart the power plant, so that's a good result. the operational tests at InSum site to mimic this or to yeah show these simulation results in reality. These are ongoing at the moment, and yeah, as soon as we have more tests, of course, we would like to share it with you. With this, I'm at the end of the presentation, and I want to mention that the GeoSmart project receives funding from EU's Horizon 22 Research and Innovation Program, Grant Agreement 848576, and here is a group picture during a site visit. Thank you for your attention.